All right, thank you. So we're back, and I'm happy to introduce Richard Howitt from the University of California, Davis.
Thank you, Steve. Is this microphone correct?
It is.
Okay. I'm continuing the cheerful topic of contaminated water and large quantities of money to talk about the agricultural effects. And we were just saying over the coffee break that this was one of the several unexpected and interesting outcomes of this study, because when we started it, we sort of both knew, of course, everyone knew quality is going to be affected by this and by the possible different solutions to the problem of the delta. But we had no idea of the magnitude of the economic importance, both, as we've just seen, tremendous economic importance to the urban sector. And now I'm going to talk about the effect on the agricultural sector and how we estimated it. So, and then the other thing is, when you're thinking about moving 4.9 million acre-feet of water south to agricultural, closed basin irrigation, or urban use, obviously quality is an extremely valuable economic component. And I wonder what went into the minds. I suspect it was a political decision as to why you would take really nice quality Sacramento water, say 100 parts per million, and you've got to move it south. So first of all, you put it into a place. To move it 40 miles, you busily mix it with seawater to raise the salinity up to 300 parts per million before shipping it south. Huh? And so fundamentally, that's the current system. Remember, you want clean water south, so you deliberately, or by mistake, contaminate it and then ship it south. So let's look at the costs of this action, since it seems to be somewhat irrational. And this is the costs on the San Joaquin Valley. And I'm just going to give a quick introduction, and without going into all the stories about Mesopotamia, Nile Delta, and the Sacramento-San Joaquin Delta, some of them slightly older than others in terms of irrigated agriculture. But one thing we absolutely know, in terms of irrigated agriculture, we are in the evapotranspiration business. That's what we're in. And if we're in the evapotranspiration business, we only evapotranspire water, and the residuals stay behind. And so this has bedeviled irrigated societies for the past 4,000 years, certainly. And we need to take serious thinking about this if we're going to have a steady state agricultural urban economy and society in the Central Valley. When we first did the first effects of salinity on the delta, we built a delta salinity model in the first PPIC report. And I finished an ongoing report which is coming out for the State Water Resources Control Board on the long-term impacts of increased salinity in the Central Valley, economic impacts. And one of the main conclusions we came to at the end of this report is that, surprisingly enough, we would say, don't give any more money to economists, give it to hydrogeologists, because we really don't know enough about the rate of salinity accumulation, its spatial variability, its dynamics, and its impacts from a strictly physical sense in the valley to be accurate. But given that, we'll take the evidence we've got. And so we're looking at how agricultural yields are reduced, how the reduction in those yields tilts the cropping pattern away from more profitable fruit, nuts, and vegetable crops towards more resilient crops. Because, of course, ironically, and expected, the crops that really make money are the ones that are most sensitive to salt. Secondly, where does this salt go? How much goes into the deep aquifer to permanently degrade this future aquifer pumping capacity? And how much accumulates perched above the Corcoran clay layer to form saline, perched saline groundwater, which further then reduces cropping patterns? We're going to measure the economic impacts by employment, income, and total output. So this is our first piece of information that we get from Department of Water Resources and the Bureau of Reclamation. And basically, this is the extent in the southern Central Valley of perched groundwater, what they call saline-affected areas. Sorry, I'm going to go back. Saline-affected areas. And these are the microsiemens per centimeter salinity, and these are the areas. And so we can see that we've got a very large area which is salt affected. And what we did to do this, we've superimposed these on a series of economic modeling zones which are called CVPM regions. And these are linked by water district, microclimate, and administrative county boundaries, although they do cut across county boundaries. And so this is our economic model runs on these districts. And we try and reproduce, calibrate it to past production patterns. The first thing we have to do is we're going to have to use GIS to break these down and find out what's the degree of salinity in which regions. And so the State Water Resources Control Board study they picked a time of 2030, and they said, if we don't take any action on salinity in the Central Valley, what will the situation be by 2030? And we looked at several different effects. There's the direct crop effect. There's the indirect crop effect of the changing crop mix on the processing industry. And then there's the costs to the processing industry of the increased salinity from their groundwater water sources. There is a cost on our confined animal industry. Remember, people who worry about population, say 1 million people moving into the Central Valley and the impacts, forget that in bovine form they're already there. There's 1.5 million cows. And the solid waste ratio, I'm told by my friends who are interested in this solid waste disposal, runs about 1 to 10 ratio of us to a cow. And so we've already got 15 million people there in cow form, plus all the other poultry and other animal operations. It is, of course, an extremely profitable major problem, the source of money. However, it turns out that the economical way of removing solid waste at the end of an animal operation really is land application. And depending on how stringent you are about the steady state nature of that, ideally you would want to see the plant material grown would actually incorporate the phosphorus and the nitrogen, not the salt, the phosphorus and the nitrogen from the solid waste, and have that removed in some way or recycled to have true disposal. So what we find is that the economic rate limiting variable on future animal operations is the degree to which the land will be available to really remove these nutrients and the acceptance rate of farmers to have that land. And this acceptance rate is really important, as we've seen if you dial back a year ago with the scares about E. coli contamination in spinach and other inputs, that this is a very tricky balance for people producing a mixed farm with a combination of field crops and vegetable crops. They've got to think about the public health aspects of this. And then finally, we've got some non-market costs and benefits which we surveyed people about. But let's go back to trying to work out what the salt balance in the valley looks like. And first of all, we've got the effect of this on yield reductions. And we're using Van Genukten and Hoffman's fundamental article on yield reduction. And it looks like this. These are what we call VG curves. And you can see they work on the proportional yield reduction as a function of the C50, which you can think of that as an LD50 or something. It's the salinity in the VADOS root zone that reduces the yield by 50%. So there's a ratio of C, the actual concentration, to the C50. And that's what's on the bottom axis. let me point here for the webcam people. And likewise, this is the relative yield reduction. So we start off with a root zone that's absolutely pristine, and we get whatever the yield is in that region. And then as we increase the salt, depending on this parameter rho, and here's some different curves for different rho values, and we're currently estimating them, we get this, we slide down this yield reduction. Initially, no effect. And then depending on the rho, you either get a gradual effect with a low rho or a very rapid fall off with a high rho. And basically, this would be where alfalfa and cotton is, and this would be where lettuce is. And so this is now we have one other really difficult complication, and that is that if you remember back to that map, that perched salt water is about 2 meters below the root zone in many places. Some places a little bit closer, some places further away. But it's not directly in the root zone, and this is directly in the root zone. And so we applied a factor, and we lowered the impact by 50% to account for that difference, because there's several actions farmers can take to offset salt both in their water and in the root zone. The first one, of course, is leaching, and then there's a switch in irrigation technology and a switch in irrigation methods. We are doing some additional research, which is not finished yet, in trying to get an empirical estimate of how effective that behavioral response to salinity is to offset it. And I can talk more about that later. But this is a major assumption in the study. And this is the sort of information we have. We have the DWR land use crops here. So we have a land use type, and then we GIS'd our salinity impacts on top of that. And so for each field, by kriging it, we have a centroid, and actually for each field, we have a cross-section. We know the soil type, the salinity level, and the crop grown. And then by grouping these, we can draw the inference of how the farmer did respond to in his cropping pattern to salinity changes, and then how they will respond to increases in salinity. So this is how we get the base response. And now let's move on and look at how we think other people have thought that salinity might change. What we're doing, and this is a very, very, and please don't ask me the engineering basis of this, but this is a very, very crude, what you might call Tupperware hydrology, in as much that you regard this as a basin with sloping sides, and you keep pouring additional accumulation of saline water in there. What regions of salinity will increase the most? And of course, it is the outside regions which will increase most in these areas. And so we took that GIS area and we took some extrapolation rates, weighted them by these factors, and you'll see that the most concentrated salts areas we actually didn't increase at all, and we increased them in inverse proportion to their concentration. Think of it as, and if you look at the Corcoran clay layer pictures, you'll see it's got a sort of a gentle slope bowl. And having done that, we then need to get the rate of change. Now, Garrett Shoops did a PhD in Davis, in which he published in 2004, and in it he took 500,000 acres of salt-affected area in the valley, only 500,000. It represents about 50% of the acreage affected. And he plotted the rate of change of the salt-affected pixels over time. So he's got these, and it really starts to kick in the 70s. So we've really got about 30 years, and we threw in these other ones out here and did a regression on them, and you can get an approximate regression, and it runs at 0.5% per year rate of increase. Now, Shoops and Hopmans also published a paper in the Procedures of the National Academy in which they looked at this 500,000 acres and did a complete balance on it. And if we look to the right-hand side, it's very fuzzy because I'm afraid we just grabbed a PDF and scanned it. But this is the total salt function running from 1940 to 2000. And if we look at this rate of change, we'll see that this is running at approximately 500,000 tons per year. 500,000 tons per year net accumulation of salt. A third study we found, and here's the curious thing, this is a major rate limiting variable to the steady state agriculture, and yet there's only 3 studies on it. Was one done by Jerry Orlob a little bit earlier in 91, and he estimates. So try to find, here we go. He estimates that it runs again this figure of 500,000 tons a year net accumulation. Now we're well aware that much of the shallow groundwater is stimulated by salt movement out of certain marine layers due to leaching and accumulation elsewhere. At the minute, we're looking at net imports because that's what's going to be affected by a peripheral canal. So we used all these to come up with some effects. And the question is, we've got the trends, and then we change that cropping mix with our cropping model and say, if the area of field crops changes, how will that put restrictions on the confined animal operations? And so we have 2 sources of money, one from crops directly and one indirectly from confined animal operations. And we parameterize these over a range of increase in salinity over our time horizon. So we're taking a 25-year time horizon, and we can go from 3% to 13%. Now remember that Shoup's mean regression puts us at about 12 to 13%. And we then put them into 2 cost functions. And so we've got the percent of saline affected land increase down here, and here, and here we've got losses in millions of dollars. Picking a figure that's most likely to extrapolate the past rate of increase from Shoup's and Orlob's and Hopman's studies, say of approximately 12% over the next 25 years, we're looking at an annual cost will increase, the annual cost will increase to somewhere about 180 million for crops per year, and somewhere in around 140 million for animal operations. So we're looking at a total cost running at approximately $320 million a year if we do nothing and let this accumulate. How does this map in? Now, we can do it in 2 ways. So if we take 20 years, and again, one of the fun things about working with my colleagues here is the interdisciplinary thing, and we were sitting around the table and saying, well, what's the significance of this? Supposing we put in a canal and we start diverting water at Hood at 100 parts per million instead of at the pumping plants at 300 parts per million. Well, how much salt will we not? And Bill Fleener said, I can do that. He says that a lot. It's very nice. And literally the next time we had a meeting, the next week he came back with some really fabulous stuff, which I'll show you. So we've got 2 different indexes here. You can either measure this in total tons of salt, and remember, Shoup's and Orlob think there's about 500,000 tons a year going in, which is costing us would cost us a little bit short of 400 million. Or you could say we move 3.7 million acre feet of water into the valley from the delta. And you can plot this on this scale, which is a fun one, because this is plotted on the parts per million, or decisiemens per milliliter, of this 3.7, because we can map 3.7. It turns out if you move 3.7 million at 300 parts per million, which we pretty much know, guess what you get? You get 500,000 tons a year. And so what you can do is you can map, if the canal can meet existing requirements, you can map this into tons, and then you can map the tons into money. And so supposing you had this same operation, but you were diverting 100 parts per million instead of 300, you would have the difference between 400 million and approximately 110 million. Hey, wait a minute. All of a sudden, this is a third of a billion. This is starting to get not real money by Washington standards, but non-trivial. So let's follow this through. You can also think of it, even if you don't like money, you can think of it as a time shift of buying time to stay in the same steady state. So let's look at the sort of the Doctor Who type time shift stuff here, and we can run these these two cost functions for animals and crops, and this is the time scale we look at. But if we can just drop it from 300 to 200, remember we're not being very ambitious, 300 to 200, we can shift time back by 10 years. And if we can drop it from 200 to 100, we can buy ourselves another 20 years to get into steady state. So you can look at it at cleaning up the water we're shipping south, trying to get rid of the salts, which is extraordinarily difficult from the Tulare Basin, this closed basin. We don't even have the San Joaquin River to dump them into. Or shifting time and buying us time to get into steady state. Well, what about this canal business? These are the numbers that Bill came up with. This is the daily tonnage of salt shipped out when you meet export requirements for the past 20 years. Bill can give you the exact date, but it was a 20-year period. And this is the size of canal. If we run them through the delta, remember the scheme we've currently got, which is contaminate the water as much as possible before sending it south to the valley and LA. We ship that out daily, 5,400 tons of salt. If we build a tiny, tiny canal for urban use only, we can still drop it by 1,000 tons a day. 1,000 tons a day. Now, note, of course, this is non-linear as we'd expect. If we build a moderate-sized canal, 7.5 thousand CFS capacity, we drop it from 5,400 to 3,700. And if we multiply this by the days, I'm going to make this number up. You can check me later. It's right around 600,000 tons of salt reduction export. Now, this model was run, and Bill can correct me. This was run with a mixture of a little bit of through delta when we can do it, and getting it through the canal when we can take it out of Hood without violating a flow rate in the Sacramento River, which I think was pegged at, is this a 10,000 or 10,000 CFS flow? And of course, here comes the nonlinearity of the canal capacity, because we can double capacity from 7.5K to 15K and just get a relatively small increase, very small increase, in the ability to export water, and a consequently extremely small increase in the reduction. But here's another interesting thing, that the three studies we have estimate and the back of the envelope water qualities know that we're shipping 500,000 tons down there. And we can cut that back by 600. Now remember, this is a net accumulation down there because we're shipping many more tons in, and then, as we're well aware, a bunch is coming out with the San Joaquin River. So it's the net accumulation, it's 500,000 tons. The total import is about 1.2 million, or something like that. But if we can reduce our net import by 600,000, then as an economist, I can sort of think about that and say, wow, that sort of balances out. Now, I know, of course, that's not true hydrologically. But people who worry about the salt in the here's the take-home message. If you're worried about salt in the Central Valley, think of peripheral canal. This is a bit weird, but it's true. So here we go. Jobs and money. Looking at money, 7.5, if we multiply all these effects of animals and crops and processing through the system, we can get costs up to 850 million a year in 2030, total costs. This would be the savings, in terms of quality savings, from a medium-sized peripheral canal. If we're looking at jobs, we're looking at 22,000. So the surprising thing to us was how big these numbers really are. Now, I think we're probably, if anything, on the high side. So I'd take these numbers with a grain of salt. But remember, we haven't even added in the urban numbers yet. And we saw in the previous talk that they're equally as high. The point about it is that there are lots of limitations to this study and lots of caveats and lots of cautions, particularly the link that we're currently working on between the perched salt water and the cropping pattern. How effectively can farmers offset that? Secondly, there's this tremendous variation in spatial variability of salts and impacts, and we've just taken a broad brush. Thirdly, we've extrapolated these three studies to the whole valley, and so you have to be always cautious about extrapolation. And we might have got our predictions of cropping patterns wrong. What we do know is that certainly even allowing for these caveats, the numbers are still, the quality component is a substantial factor. And that the other thing would be interesting is that economists tend to look at unintended consequences. And so if one has a canal, and if it gets financed the way it's going to have to be financed, which is those commercial users who use the water to make money have to pay a proportion of it, it's going to increase the cost of water in the Central Valley, no question. And what's that going to do to the cropping pattern and the drainage? It's going to also cut back drainage. And so we'll get a double whammy. We will import much cleaner water with a reduction of salt load, and we will also put an incentive structure, again, with a lot of complaining, of course, in place that will encourage conservation and minimize drainage flows, which will further reduce the accumulation of salts in these shallow groundwaters. So we're looking at substantial quantities of money in the future if we don't do this, or if we do it, we can save it. Even the small facility, a very small facility, can make a substantial difference. And a medium-sized facility can offer substantial quality benefits. And so there we are. Questions? Ellen.
Just wanted to add, Richard, that you said you think maybe the numbers are a little bit high, but in contrast to the drinking water study that we just heard about, you're not actually factoring in sea level rise. So no. From that perspective, it's probably conservative, right, in terms of the salinity impacts. Right?
Thank you for pointing that out. Bill's model ran with the standard sea level rise. It's not in there yet. Yes.
Did you take into account at all with the cleaner water leaching of the soil or the salts in the soils?
Inasmuch with cleaner water, we'd get actually more uptake of salt as they went through the same level of strata of soils, old marine soils on the west side. No, I didn't. And so what you're saying is you put cleaner water in, but you still get as much salt in the drainage. Yeah. That's certainly possible. But we were only actually looking from a plant's perspective, and we didn't calculate the increased load.
But you should also have less application of water for leaching.
Exactly.
So
so that might offset it.
Works out yet.
I think it quite likely that given if we are even cutting the ag contractors a break on the cost of a peripheral canal, it's still going to add $100 an acre foot or something like that. I mean, 70 or $80 an acre foot to the water costs for that proportion of water that comes through it, and that in of itself will be a substantial incentive to adopt lower drainage generating technologies and methods. If you want to have a look at the possible effect of this, just have a look at the Shoup and Hopman's PNAS paper, and you'll see that during the drought, and we'll see this year, our forecast that 2009 will be a really low drainage year. Why? Because the current price of water in Westlands Water District is running $300 an acre foot. And you're going to put that stuff on very carefully. And so what we're going to see in 2009, because of the restrictions, is a little preview of how we're going to be operating every year in 20 years' time, perhaps. So we have a double effect. There'll be the scarcity cost and the real money cost of water effect on drainage, and then there'll be the quality of the water itself, which will be lower leaching fractions. Steve?
Well, I liked your characterization of that you're managing evapotranspiration, and I've spent a fair amount of time making evapotranspiration measurements, so I'm assuming that the crops that you're talking about use somewhere between 3 and 5 feet of water per year. And if you were able then to use less water because you didn't have to flush the salts out, have you done some estimates as to how much water you would also save in the Central Valley by going with a lower salinity water as an application water?
Not yet, although we have done a climate change study in which, of course, with the increased temperatures that we are anticipating, you actually get a slight increase in evapotranspiration per unit area. And actually, we've shown that the crop yield goes up because of technological change and ET. The water use per acre actually goes up also, but not as much as the crop. And so the water use per ton of crop grown goes down. But we've got to be very careful because we always think of per acre. And then if you look at the rates of technological progress in terms of yield per acre and yield per unit water, that's also got to be figured in.
But you do have the opportunity to change the amount of water that is actually going to go into E versus T versus drainage.
Absolutely. I'm confident that the farmers, being smart operators and businessmen, when they see both the scarcity cost and the fiscal cost of this water, will definitely do that. They've done it in previous droughts and in the 2009 drought, which we're definitely going to be facing, regardless of the rain. They will do it again. They won't be happy, they won't like it, but they'll do it.
I had a question that relates to the nature of your interaction with the various communities that you're sort of characterizing in this model. In the last presentation, I got a good sense that there was a lot of conversation between your research team and the treatment operators, the treatment plant operators. It sounded like you went directly to them for a lot of your characterizations and sort of reality check. Could you characterize how you did that with your study? Are you working with that kind of relationship with the producers and the growers and that kind of thing, or are these reported numbers mostly?
Mostly reported numbers. We did, in the Water Resources Control Board study, do a primary survey of around 700 people in the valley. Mainly we were asking them how they felt about salinity, how salinity affected their households, how salinity affected their lives, and we actually asked them what would you pay to have salinity improved in the valley, and the answer was $4.70 per person per month. If you want to know what it is. We did an extensive primary survey mail survey of people for that, and that's published in the other report. In terms of, we did not go out to the water districts and say, if you got cleaner water and if you were charged more for it, how would you change your operations? I'm more a believer of seeing what people do rather than what they say they'll do. You know, I mean, we've all got. I had a phone call last night asking me to subscribe for the nth time to a charity, and you know, I said, and it's always when you're trying to cook dinner. And I said, oh yeah, okay, we're doing it. We do it by mail. You know, I gave it the office reply.
Can you just clarify for me you described you in the description of the database, the GIS database with the fields and the practices, and could you clarify for me the period of time on which that empirical model of response of cropping to changing salinity was built?
Well, it's built from 99 to 2004 in terms of our database.
Okay.
But the actual response is a cross-section response, because what we wanted to do was statistically break out the effect of farmers on salt. And so we wanted to shake out the effects of changes in price, changes in technology, changes. We said, okay, let's just take a snapshot. And so we picked for a corner of Kern County, which we call CVPM 19, which we can show you. And that had 2,700 and something fields in it. So it's a decent sample. And we broke them into different salinity slices. We actually ended up with 30 different salinity slices, different numbers of fields and then we looked at the cropping pattern, and we said, and we compared it to a time series for the whole county of the riskiness of the cropping. And we said, I believe farmers are like Wall Street. No, they're better than Wall Street managers. They have portfolios, and they have portfolios in real things instead of imaginary instruments that don't have any backing. And they run a portfolio of crops. And you'll go to any farm business, and they won't be just all in lettuce or all in pistachios or all in alfalfa. They have a portfolio. And that portfolio is for various reasons, one of which is to offset the risk of price and yields. And some years are good for some crops, and so on and so forth. So we took that, and we said, if a person changes their portfolio, they must be expecting, if the risk is constant, the risk is not a function, price risk and yield risk is not a function of salt. They must be expecting a lower average yield. So what yield loss would induce the people to go out of high-value crops more and more and more into low-value crops? And we saw at some of the high levels that the high-value crops are driven out completely. The classic example is a study done on Broadview Irrigation District when they had their drains blocked up for a 15-year period. And the cropping pattern that used to heavily depend for money on the growth of processing tomatoes went out completely during that time. And then they unblocked the drains because of the change in the law, and guess what? Tomatoes walked back into Broadview. And then they got blocked up again, and they've walked out again. And so we used the pattern of crops to tell us, and the interesting thing is that farmers, we looked at the marginal probability of observing a crop in a salt zone, and that changed just as if the farmers had come up and talked to the theoretical salinity people in Davis and said, tell me, how sensitive are these crops? And they'd been given the list of sensitivities and gone back and, no, these guys had figured it out for themselves. That's real observations. So anyhow, that's a long answer.
I understand it a lot better, thank you.
Yeah.
I have a question about your one table. I want to make sure I understand it correctly. But when you looked at the loss by 2030, I think, using various water supplies, and it doesn't go down to zero. It goes down to like $100 million a year.
Sure.
And so does that mean, I mean, make sure I understand it correctly, does that mean that there's there's still some salination, yeah.
Of course,
So
yeah.
so even if you go to Sacramento River water, you still have a
Sure,
salt problem.
we've still got 3.7 million acre feet with 100 parts per million going south, and you've still got salt accumulating. If you believe the Orlob study and the Shoops and the Hopman study, and if you don't improve conditions on the San Joaquin, and you still let the San Joaquin remove the level of salts it's moving now, because that's really the only outlet, then you have to say the net accumulation is 500,000 a year, and we could offset quite a large proportion of that with a canal. But we've still got salts going down there because we've still got losses because, and we've still got a salt problem because of the mobilization of salts that come from the upslope subsurface marine soils down into the trough, as it's called.
So, I mean, do you eventually get to a sustainable situation? You said steady state. What do you mean by steady state?
We can get, I believe, and this is another thing that I've changed my mind on, I believe we can get to a steady state irrigated agriculture through two broad effects. One is to downsize the acreage, and that will either happen forcibly by salinization or voluntarily by economics or environmental buyouts or something, and improve improve the quality of the water being imported into the valley such that the net increase in salt burden is greatly reduced or perhaps eliminated. Now, these numbers, these very crude initial numbers, suggest that that's feasible if we have an alternative delivery system. Under those circumstances, the net, we're able to net steady state. That doesn't mean to say we won't still get accumulation because we've still got those marine subsurface layers up on the benches on the west side, and that's great soil. It will continue to be irrigated, and we will continue to get movement of salts, and there's a big reservoir of salt movement there, which I think will continue to build up. But there's hope. And it's not in the direction of, interestingly enough, it doesn't require an additional drain. We've got to still use the San Joaquin River as the existing drain, but maybe we can put more water into San Joaquin and do the dilution solution.
So, Richard, that discussion has to do with the San Joaquin Valley as opposed to the Tulare Basin.
Yes. The Tulare, as I understand it, is really a closed basin. And so we have to have alternate salt, and we have alternate salt removal systems there. And they will have to be, of course, evaporative ponds, stockpiling, and we'll build another theme park with Salt Mountain. Any other questions? Okay.
Richard, I just want to raise a dilemma for you. So, you mentioned how this was one of our surprising findings, and at one point in the report we talk about this as it's kind of a windfall. But both the water quality, the water treatment savings for drinking water, but also these savings for agriculture, and we actually suggest as one of the sort of to look at this as one of the possible ways to help finance, say, ecosystem investments in the delta. And in the case of drinking water quality, you can think about this as it's pretty straightforward to figure out how to charge people because you could just do a per acre foot kind of fee. But in this case, given the maps that you showed us and the discussion about these slopes and drainage and everything, I'm guessing it's going to be a lot more complicated. And just wonder if you have any thoughts about how one might go about figuring out a way to charge farmers for this windfall.
Well, one way, which might be simpler than trying to reduce it to dollar terms, would be to go back and say, okay, how much less water will you be applying because of the change in the leaching fraction and so on. And if this land goes out of production, instead of pouring the water back into the existing regions, that water has to go back into the San Joaquin River. And I haven't done any calculations yet, but if that water went to, or some other environmental purpose, but if you put it in the San Joaquin River, you could, in fact, I think, internalize it by pointing out to the farmers that the San Joaquin River is their only salt removal mechanism that's legally and politically available to them at the minute. And that if they, and currently, one of my colleagues, two of my colleagues, Peter and Bill, and maybe some of the rest, want to see the salmon runs restored on the San Joaquin. And there's no question we need more water in the San Joaquin. We're going to have more water. But if we have more water and we can still improve the quality, so you would say the salt load stays constant, that can't be increased, but the addition, any water savings goes towards improving the quality of an environmental amenity. And if it's an environmental amenity that enables farmers to meet the environmental standards more cheaply, that would have some positive incentive for them rather than a tax and a negative incentive. So what I would do is actually I would try and hit the urbans up for all that money I can calculate that they're saving. And for the ags, I wouldn't try and get into the money business. I'd try and get into the water business and try and move that water either not being diverted from, it wouldn't be diverted from Southern Delta, we'd leave it in Delta or in the San Joaquin, whichever. And I think we could sort of work towards doing that calculation, but we haven't done it yet. Okay? Thanks a lot. We're on time.